So this is a continuation of basically yesterday's lecture. We mainly focused on number one, but number one was a little bit different for us because we looked at how to calculate energy stored transferred by a spring. That was worksheet number 2-ish that we just went over in class today. However, now what we're going to be able to do is we're going to expand this out to the other forces that are out there. So that's going to be the major one there. That's the biggest idea. From there, what you're going to see is those equations. There's going to be a whole bunch of those equations for number two. You need to know when they work. You need to know how to use them. You need to know how to apply them. So really number two falls under an interesting aspect where you just need to understand them and why that works. So make sure you are putting a focus on that. And of course, number three, we're going to talk about this idea of work. We've been actually doing it, and it's going to be applied. We're going to see if we're going to be able to get to that, though, today. So first off, number one, how to calculate energy stored by other forces. So the first force that we are going to start with here is actually Fg. So in order to calculate energy stored or transferred by a force, the goal, as we talked about yesterday, is going to the proper graph. And in this case, our graph is going to be the Fg. And what's interesting about this is I would normally say delta x, but in this case, what actually affects Fg, it is going to be delta y. You could also refer to this as height. I have no problem. Those two both go hand in hand. Now, a question that I can ask is, what happens to Fg? Again, this is near the surface of the Earth. So this equation will work only near the surface of the Earth. What happens to Fg as you increase the height? Does it increase, decrease, or stay the same? And so, thinking about this one, hopefully you realize, wait a minute, Fg doesn't change. It doesn't matter if I'm at ground level or if I'm 10 meters in the air. Does Fg change? No. So this graph looks pretty nice and easy for us. No matter what my height is, Fg is staying the same. That should be a nice horizontal line. Should I redraw that? Yeah, all right, fine. So let's try that again. Nice horizontal line like this. And what we learned yesterday, the area of this graph is the energy transferred or stored by that force. So what we can do here is we can be clever with our colors and say, yeah, let's try a new color here. We can go in here, rope this off, take a look at this area right here, and I can say this area will represent the energy. And the energy in this case is not going to be ES, it is going to be EG, the energy stored gravitationally, because what force are we looking at? We're looking at gravity. So this is going to be equal to EG, and you can get this equation very easily now by just going through and saying, well, how do I get the area of this graph? It's going to be base times height. So we have Fg times h, or Fg times delta y, whichever one you'd like to use. And of course we can simplify this out a little bit better. We can say, wait a minute, hold on, I know Fg. Fg is going to be equal to our 9.8 newtons per kilogram times our mass. So we can rewrite this as 9.8 newtons per kilogram times mass times height. And so the equation that I'm really looking for, the one that I'm going to box in, the one that I'm going to give you on your equation sheets, this is the most common one. Right there. This is again taking a reference point of 0 as being no height, no EG. Any questions with that? So very easy equation, first one to start off with that we can get Pretty simple. The other one that we actually have to focus in on, that is FG. What we can do is now we can take a closer look at another graph that we can create. And it is going to be a graph that is going to look at an object that is being pulled. So we have our object here. We're going to pull this on a frictionless surface. And we are going to apply some force to it. We're going to call that just F. And so if this object were to start at rest, V naught is equal to 0, what we can do is we can actually now go through and say, well, the longer I pull this box, the more it's going to speed up. So the force is actually going right into the speed of this object. And so what we can do is we can actually go down into the good old F, the force that I am applying, through some delta x that I am applying it by. And sure enough, if we looked at this graph, I'm going to keep this force constant. I'm going to keep pulling it at a constant speed. And so what we're going to do is we're going to see a graph come out here that is going to be, again, a very nice flat-lined graph. If you can draw this graph, it's then really simple to now go through and say, oh, I want to take the area of this. Let's go pick another color. So we can go in here. We can rope off some ending to that graph, and I can say the area here, the area of this graph, is energy that is being transferred into the box. And of course, I'm going to ask, what type of energy is that being transferred into? No, it is on a frictionless surface. It is not E internal. Got to be careful. Yeah? EK. This is a box that is going to now be in motion. It's going to have a velocity. So what we can do is we can say all of this energy from this force that we're looking at is going to be F times delta x. Now, is this a general equation that I can always use? No. However, we can modify it a little bit so we can actually calculate some of this energy very easily from here. First off, this force, this F, is actually the net force which is causing the acceleration, which is equal to the mass times the acceleration. Good. So we can now go into this and we can say, oh, wait a minute, the area again is going to be EK, and this is going to be equal to MAX, max. However, is this a general equation that is going to work for us? No, because acceleration is sometimes really hard to get. Delta x isn't like the nicest thing to have. So what we are going to do is we're going to have to do a few substitutions here. The first substitution that we would like to perform is the good old A. A can be substituted as something that we know, the good old delta V over delta T. As long as it's a constant acceleration, this works. This is nice. It's a very nice, easy substitution. The other substitution that we want to take a look at is delta x. And what's really interesting is I'm going to make a substitution here that will make sense because we're going to eliminate as many variables as possible. The substitution I'm going to put in here is the good old delta x equals v plus v naught over 2 times t, or delta t. And the moment I do that, again, you do your fist pump because you love math. Math is so great. This is the greatest thing about math. What's going to happen? Oh, you guys don't love math. Sad. Delta t cancels. So you see this and you start writing this out. You start realizing you have m times this delta v over delta t, and then we write in the v plus v naught over 2 times delta t. You realize, oh yes, t. See you later. So T is no longer an issue with energy, which is kind of cool to see. The other cool thing about this is V naught is actually 0. So we call that 0. Delta V is, remember, V minus V naught. That becomes 0. And you get left with an expression that is EK that is going to be equal to the energy transferred into this box. Any box that is moving can actually be written as 1/2 mv squared. Box that sucker in. And so now at any given moment, if an object has velocity, we can calculate it by going 1/2 mv squared. And what's also really nice about this is this actually works if an object is not necessarily accelerating at the same rate. It can be having a variable acceleration, and this will still work. So that is our second equation that we get. And you start to realize we have really only one other equation per se that we can solve for. And that equation will be for E internal. And this is a really easy way of solving this one. It happens more often than not. Let's zoom in here and take a look. If you have a box that is already moving and there is friction, if we were to draw a force diagram for this box, you're going to realize that you have Fn going up, you have Fg going down, and you have your good old FFK holding it back. That FFK is going to happen across a distance, and that FFK is going to create heat. It's going to create our E internal. So if we drew our graph again, we would have FFK hanging out on over here. We would have delta X because this box is traveling some distance, which we call delta X. We can draw this in on over here. Start to realize that, oh, hey, take a look. Take a look at the area here. This area represents E, in this case, internal. And that area is easily calculated as FFK times delta X. So I am going to box this equation in. This is nice. This is handy. Anytime you have any E internal. However, I need to put a big star here and put a big emphasis. This is only E internal caused by friction. This is only for friction. You cannot do this for sound. You cannot do this for any type of vibration or anything else. This is purely if friction is the only major heat source that is causing E internal. FFK times delta X. So, zooming out, you start to realize, what did we really just do there? We created three equations. We got that guy, and we got this guy. We also have the one that we learned yesterday, the ES is equal to 1/2 K times delta X squared. And with these four equations, we can start to go into our LOL diagrams and start figuring out numbers. And that's going to be the major source of everything that we see in this. Any questions with that? So this lesson really was based around, let me go back on over here, is really based around number 1 and number 2. Number 1 being, I know and understand how to calculate energy stored transferred from other forces. Key idea here is, how do you calculate energy? How do you calculate energy? It's always taking the area of the F versus delta X graph. You have equations now that are generalized for that, but the key idea is you can always go to that F versus delta X graph. The other one that you see is I can understand and use the energy stored equations. Make sure you know where they come from. Make sure you know how they're used. Make sure you do not use them in the wrong places. This sometimes happens. You got to be careful about that. And number 3, this will be a preview for tomorrow. I can properly select my system to calculate work done by a force. Actually, you know what? No, time out. This is going to be your homework. Your homework is to go home tonight and watch this video and take notes on it. We are going to do the flipped classroom on this one tonight. So go home. I can select my system Or I will do another video after this one on YouTube. You will see it there. I can properly select my system to calculate work done by a force. It will be a short, I'm thinking 5 to 7 minute video. All I'm asking you guys to do is go home, watch it, take notes. Come in with those notes tomorrow. I will quiz you on it. How? Probably a clicker quiz.
How do you find the video?
I showed you at the beginning of the class. Blackboard. Log on to Blackboard, find the link, click on it. It's under announcements. It'll be there. Ooh, that's going to be fun. Do it. Thanks for listening.